Well, yesterday we talked about how to determine how much energy an electron had if it was in a specific Bohr orbit. It goes to follow that if you have an electron in a specific orbit, that you should be able to boost that electron up to a higher orbit if you give it more energy. Similarly, if that electron would go from a higher orbit to a lower orbit, it would then give off energy. And it is important for us to be able to tell how much energy is either absorbed or given off when an electron changes its level in the Bohr orbits. And anytime we calculate a change in something, we're going to use the Greek letter delta. You've seen this in some of your science classes before already, I'm sure. In fact, we did it when we talked about change in temperature, when we did calorimetry calculations in first year chemistry. If you've taken physics, you've seen this a lot. The important thing to remember here is that when we calculate the change, we're always taking the final minus the initial. Because if you get them backwards, get them flipped around, the sign on this energy is going to be different than what it should be, and then that will end up affecting some of your calculations. So the thing to remember is that if you're going from a higher energy level to a lower energy level, initially it starts out high, but then the energy level ends up low. And so you're going to be subtracting a bigger number from a smaller number. And so that means that the electron is actually going to have this number over here as far as change of energy is going to be negative because the electron had to give off energy. If it absorbs energy as it goes to a higher energy level, then this number will be positive. Now, when you look at this equation, again, make sure that you don't make a mistake when you copy the equation down, because even though delta E is the final energy state minus the initial energy state, if you recall in the equation that we learned yesterday, there was a negative sign in front of it. And so we took that negative sign out, but we also flipped this initial and the final. And so I don't have that negative sign here, but that means that these two are now backwards. So just it's something to be aware of and to watch out for as you're working some of these problems, okay? One thing that I want to point out is that as you are discussing when an electron may be changing orbits, there's not necessarily just one path. So here I have a series of 4 Bohr orbits drawn. And let's say, as an example, that I have an electron in the 4th orbit. It is possible because everything in nature seeks to be at the lowest energy level. It seeks to be in its ground state. And so it is possible that this electron will drop from the 4th all the way directly down to the 1st energy level. That could certainly happen that way. However, it is also possible that this electron could drop from the 4th to the 3rd, and then once it's in the 3rd, it could drop all the way down to the 1st. Or if it goes from the 4th to the 3rd, it could drop to the 2nd, and then it could go down to the 1st. Okay? It could also drop from the 4th down to the 2nd, and then go to the 1st. So there's a lot of different ways that this electron could get from the 4th orbit down to the 1st orbit. So if I kind of look at the overall sum of what could happen, I could go from the 4th to the 1st. I could go from the 4th to the 3rd, or it could go from the 4th to the 2nd. So any of those are a possibility. If it's in the 3rd energy level, it could go from the 3rd to the 2nd, or it could go from the 3rd to the 1st. If it goes down to the 2nd energy level, it's going to then have to go from the 2nd to the 1st. Okay, so I believe I've got here all of the different possibilities that could happen. So if you look, I've got from the 4th to the 1st to the 2nd or the 3rd. I can go from the 3rd to the 1st or the 2nd, and I can go from the 2nd down to the 1st. So I actually have 6 different pathways that the electron could take as it's making its journey from the 4th orbit all the way down to the 1st orbit. Again, this is something that's going to be important as we get into why we're discussing all this even to begin with. So for a better example of why, just hang on a little bit longer. I do want to do a quick review of light, and a lot of this is stuff that you've covered in your first year class, so I'm going to go over it quickly. If you need more explanation, go back to your first year book and look at that. You'll remember that the electromagnetic spectrum is, it includes not only visible light, but it also includes energy that we can't see. It includes infrared, it includes microwaves, it includes radio waves, it includes ultraviolet light and X-rays and gamma rays. These all have, because they all fall within the electromagnetic spectrum, all of these light waves have the same speed, which is 3.00 times 10 to the 8th meters per second. But each wave is going to have its own wavelength and its own frequency. The frequency and the wavelength are related by this equation here. Frequency equals the speed of light over the wavelength. When he initially shows you this equation in here, he has a V on the top. You're more commonly going to see it with a C, and he does seem to pull that out of his hat a little bit later on, but he doesn't tell you where it comes from. So this is where it comes from. C is actually the speed of light, and so this is the equation that you'll probably want to use all the time. Remember that a wave has crests and it has troughs. The wavelength is the difference the distance from one crest to the next crest, and that's where the meters is going to come in. The frequency is how many waves pass by in a second. So it's waves per second. So seconds in the denominator, and the unit for that is also hertz. So that is this equation that you'll need to put on your card also. You also need to be able to calculate the energy of a light wave. And so the energy is directly related to the frequency by Planck's constant, which is 6.63 times 10 to the minus 34th joule seconds. Okay, so again, another equation, another constant. You'll need to have all of these on your card so that you can utilize them as well. There's one other thing that he throws in here. He uses it in a couple problems and he doesn't require it in others, but basically 1 meter is the same as 1 times 10 to the 9th nanometers. And a lot of times we tend to give the wavelengths of light in nanometers just because they're nice, easy numbers to work with. It's like 512 or 360. And so we're not dealing with big exponents or anything like that. And so it's just a little bit easier to read, but they are related to meters and you can convert them back and forth. The relationship here that you need to keep in mind, we're going to be focusing on the visible part of the spectrum, which is Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. Everything in the spectrum, radio waves are going to have the longest wavelength, and so that means that of the visible spectrum, red is also going to have the longest wavelength. But as you can see from this equation, wavelength and frequency are inversely proportional. So while red is going to have the longest wavelength, it's also going to have the shortest frequency. Okay? And then when you have the shortest frequency, you can see that if the frequency is going to go down, the energy is going to go down as well. And so lowest energy is going to be on this end as well. And so these 3 characteristics are going to characterize the red end of the spectrum. So again, that's just a relationship there that you want to keep in mind as we're working through some of these things. Now, why is all this important? Well, we can actually identify what elements may be present in a sample by exciting the electrons and then seeing what colors are given off as they fall back to the ground state. Now, something to remember is that they may be giving off energy in all different areas of this electromagnetic spectrum. These are the ones that we focus on because these are the ones we're able to see, obviously. But it is possible that they could be giving off ultraviolet light, they could be giving off infrared light, they could be giving off any of these, but we're focusing on the visible spectrum. And so if you use a spectrophotometer, you can excite the electrons, or you can just shine light on it and see which colors are absorbed. There's both kinds of spectroscopy. And so by doing that, you can see in this equation that each particular element is going to have its own characteristic energies given off as these electrons fall from one orbit to the next, because each particular element has its own specific atomic number. And so he gave you some pictures in the book of some examples of what different elements look like when the electrons are excited and they fall back. What we're going to be doing then is we want to be able to calculate the amount of a change of energy when something falls from one orbit to the next. So we're going to look at example 2.2, and it says, what color of light is emitted when the electron of a hydrogen atom moves from the 4th Bohr orbit to the 2nd Bohr orbit? Okay, so this is the equation that we're going to be using right here. And the first thing I'm going to need to find is the change in energy that's going to happen. I need to use Rydberg's constant, which we learned yesterday what that is. So I've got 2.18 times 10 to the minus 18th joules. And because we're specifically talking about a hydrogen atom, the atomic number for hydrogen is 1. So that's what's going to go in for the Z. So I'm going to have a 1. And then I have to get my initial and my final energy or orbits in there. And it says it's going from the 4th to the 2nd. So, right, from the 4th to the 2nd. So the initial is the 4th. So I'm going to have 1 over 4 squared minus 1 over 2 squared. Again, as you're doing this, be very careful that you get them in the right order so that that number ends up positive or negative the way that it should. Another trick here, when you're punching this into your calculator, this is a great place to use the parentheses on your calculator so that you're not having to do all this separate and then you have to write it down. That's what those parentheses are on there for. So here you would type in this number. You probably wouldn't type in the 1 because you're multiplying by 1 squared, which is just 1. But then if you hit the left parentheses and then you hit 4 and then the inverse key and then the square button, minus 2 and then the inverse key and then the square button and then the right parentheses, and then you hit equals, then you'll have the answer to the whole thing. Okay, so make sure that you're using those keys on your scientific calculator to your best advantage. All right, when you do that, you should come up with, should be a negative number. It's going to be negative 4.09 times 10 to the minus 19th joules. Okay, now why is it negative? Well, it's negative because it went from the 4th Bohr orbit to the 2nd Bohr orbit, and that means it had to lose energy. It gave off energy, so that number should be negative. That's a check you can do in your head to make sure that you plugged everything in correctly. However, the question is asking us what color of light was emitted. Well, in order to find what color of light, I have to know what wavelength it was. Well, in order to find the wavelength, I've got to be able to use this equation. I can't use this equation until I know frequency, and I'm going to find frequency by using this one because energy is actually what I know. So the next step then is to use E equals HF. Now, just because this is negative here, it's not going to be negative when I put it down here because this is the change in energy, but what I want to know is what the energy is of the light that's being given off. It possesses a certain amount of energy. It's not a negative energy that the light possesses. So when I plug it into this equation, it is now going to be positive. 4.09 times 10 to the minus 19th joules equals, remember that H is Planck's constant. So this is 6.63 times 10 to the minus 34th joule seconds times the frequency. And just a simple division problem here. And so then when you do that, you're going to end up with 6.17 times 10 to the 14th hertz is what your frequency is, because you're taking joules, you're dividing by joules per second, so the joules cancels out, Seconds ends up in the denominator, which is what hertz is, okay? Once you have hertz, you can then plug that into the equation which has the speed of light in it, and then that's going to be able to give you the wavelength. So F equals C over wavelength. Frequency, 6.17 times 10 to the 14th hertz equals 3 times 10 to the 8th meters per second. This does have two significant figures over wavelength. And then again, you've got enough experience in math, very simple problem there to do. And so that's going to give you 4.86 times 10 to the minus 7th meters is going to be the wavelength, which is the same thing as 486 nanometers. Now it did ask you for the color, and so if you look at the visible spectrum diagram that he gave you in there, you can see that at 486 nanometers, that ends up being kind of a blue-greenish color, okay? He did change it to nanometers here. Be aware that in the answer keys, he does not always. Sometimes he leaves it in meters. If you have an answer in meters and he gives it in nanometers or vice versa, either answer can be counted correct. So don't fret about those little things like that, okay? So that is the topic of how we can calculate how much energy is lost when an electron changes orbitals, as well as why it's important.